Various types of biomass serve as feedstocks for producing diverse end products. Today, first-generation biofuels, derived from edible sources like oils and sugars, are widely used around the world, with bioethanol and biodiesel being the most common. However, because these feedstocks can compete with food production, there is a growing shift toward nonedible alternatives. Lignocellulosic biomass, which includes agricultural residues, forestry waste, defatted seed cakes, and invasive terrestrial species, is used to produce second-generation biofuels. In contrast, third-generation biofuels are derived from algal sources, such as microalgae and seaweed. Although they show potential, both second- and third-generation biofuels are still emerging in the global market. The conversion efficiency of biomass into biofuels, chemicals, or materials is determined by its chemical composition and structure. Therefore, a thorough understanding of these characteristics is essential before employing biomass in any conversion application. This video shows different methods of biomass characterization to understand biomass feedstocks and evaluate their suitability for a particular conversion process. In addition, it presents the results of more than 1,000 samples. The Proximate analysis provides the gross composition of biomass by quantifying moisture, ash, volatile matter, and fixed carbon. Moisture content represents the presence of water in biomass, and it is given as a percentage of the material weight. There are surface and inherent moisture. The surface moisture is present outside the cell walls, whereas inherent moisture is within the cell walls. Moisture content is an important parameter. It affects the biomass transport, conversion performance, and product composition in the biomass conversion process. The moisture content in biomass must be reduced to achieve effective transport. Economically, there is usually a limit in the transport of biomass over longer distances. Ash content represents the quantity of the solid residue left over after the biomass sample is completely burnt. The ash content of biomass varies significantly. It is naturally formed within the plant's cell wall as a result of the photosynthetic process. However, it does not necessarily come entirely from the biomass itself. It can come from soil contamination during the harvest and collection practices. Ash can contain silicon, aluminum, titanium, iron, calcium, magnesium, sodium, potassium, sulfur, and phosphorus. The melting behavior of ash is influenced by its composition. Volatile matter content is the content of condensable vapors and permanent gases, exclusive of water vapor, released from biomass when it is heated. During the determination of volatile matter, a part of the organic carbon is transformed into a carbonaceous material called fixed carbon. Fixed carbon is the solid combustible residue that remains after removal of volatile matter from biomass. The determination of proximate analysis is relatively easy. For wood, the ASTM standard E870-06 can be used to measure the proximate analysis of the biomass. Separate ASTM standards are applicable for determination of the individual components of biomass. Moisture, E871 for wood fuels. Ash, D1102 for wood fuels. Volatile matter, E872 for wood fuels. Since fixed carbon depends on the amount of volatile matter, it is not determined directly. It is determined by difference using the values of moisture, ash, and volatile matter determined. However, the fixed carbon in proximate analysis differs from the carbon measured in ultimate analysis. Thermogravimetry analysis was proposed as an alternative method to determine the moisture, volatile matter, fixed carbon, and ash content. It has the advantage of saving time. The TGA method for proximate analysis can be described as follows. A small weighed quantity of biomass is placed in a crucible without the cover, heated with a rate of 15 to 50 degrees Celsius per minute to 105 degrees Celsius, and held isothermal for 3 minutes. An inert gas, such as argon, flows through the furnace. Then, the sample is heated by a ramp of 50 to 100 degrees Celsius per minute until 950 degrees Celsius, and then a cooling process follows with a rate of -50 to -100 degrees Celsius per minute until 450 degrees Celsius. Subsequently, the flow gas is changed to an oxidizing gas, such as oxygen or air, and a heating ramp starts until 800 degrees Celsius, where the sample is held isothermal for 3 minutes. The figure roughly shows the weight loss as a function of time and how the percentage of moisture, volatile matter, fixed carbon, and ash of the biomass sample can be determined. TGA offers further insights into reaction mechanisms, kinetic parameters, thermal stability, and the heat of reaction. The figure shows ternary plots displaying the composition of ash, volatile matter, and fixed carbon in dried biomass samples across 4 categories: forest biomass, agricultural biomass, algal biomass, and biomass derived from domestic and commercial waste. The samples from forest biomass show high volatile matter and low ash content. The samples from agricultural biomass exhibit high volatile matter and slightly higher ash content compared to forest biomass. The samples from algal biomass show lower volatile matter and high ash content. The samples from biomass derived from domestic and commercial waste display highly variable composition, likely due to the diverse nature of the waste streams in this category. This biomass category shows high ash content and moderate to high volatile matter. The elemental composition is typically complex, consisting of 6 major elements in the organic phase: carbon, hydrogen, nitrogen, sulfur, chlorine, and oxygen, and 10 major elements in the inorganic phase: silicon, aluminium, titanium, iron, calcium, magnesium, sodium, potassium, and phosphorus, which are crucial for ash characterization. Additionally, trace amounts of heavy metals are commonly present. The ultimate analysis reports the elemental carbon, hydrogen, nitrogen, sulfur, and oxygen composition. Carbon is the most important component of biomass. Its concentration is positively related to the heating value of biomass. Hydrogen is the second most important component of biomass. It contributes to the energy content of biomass. The content of sulfur is typically low, which is beneficial for thermochemical biomass conversion processes. At certain sulfur contents, extra gas cleaning steps are required in the conversion plants before the gas can be used further for other applications to avoid corrosion. The amounts of nitrogen and oxygen content affect the biomass end use, like carbon and hydrogen, but in the opposite direction. The determination of the ultimate analysis is relatively difficult compared to the approach of the Proximate analysis. The following ASTM standards can be used for the determination of the ultimate analysis of biomass. Carbon and hydrogen can be determined via E777 for refuse-derived fuels. Nitrogen can be determined via E778 for refuse-derived fuels. Sulfur can be determined via E775 for refuse-derived fuels. Oxygen is usually estimated by difference using the values of carbon, hydrogen, nitrogen, and sulfur determined. The figure shows the Van Krevelen diagram for forest biomass, agricultural biomass, algal biomass, and biomass derived from domestic and commercial waste. The hydrogen-to-carbon and oxygen-to-carbon ratios provide insights into the chemical composition of the biomass. Higher hydrogen-to-carbon ratios generally indicate a higher proportion of hydrocarbons, while higher oxygen-to-carbon ratios suggest a greater abundance of oxygen-containing functional group. Forest biomass exhibits a relatively consistent cluster with a few outliers. Agricultural biomass displays similar clustering patterns to forest biomass, also with notable outliers. In contrast, algae biomass has a broader and more scattered distribution, indicating greater variability. Waste biomass demonstrates clustering comparable to forest and agricultural biomass, but features distinct outliers. The figure visualizes the elemental composition, carbon, hydrogen, and oxygen plus nitrogen plus sulfur, of forest biomass, agricultural biomass, algal biomass, and biomass derived from domestic and commercial waste. Forest biomass has a more stable composition compared to other biomass categories. The data points for agricultural biomass are similarly distributed to those of forest biomass but show slightly more spread, especially in the oxygen plus nitrogen plus sulfur direction. Algal biomass exhibits a higher oxygen plus nitrogen plus sulfur content compared to lignocellulosic biomass, likely due to nitrogen from proteins and sulfur from certain biochemical compounds. Biomass derived from domestic and commercial waste shows the most scattered distribution, indicating high compositional variability. A wider range of carbon and oxygen plus nitrogen plus sulfur content suggests a heterogeneous feedstock, including plastics, food waste, and paper. The CHO index is introduced as a measure to represent the oxidation state of organic carbon in organic materials. CHO index equals 2 times molar fraction of oxygen minus molar fraction of hydrogen divided by molar fraction of carbon. Higher values of the CHO index indicate more oxidized compounds, while lower values represent more reduced molecules. The figure presents the distribution of CHO index values for forest biomass, agricultural biomass, algal biomass, and biomass derived from domestic and commercial waste. Within each biomass category, there is significant variability in CHO index values. The CHO index values of forest biomass are around neutral to slightly negative, indicating a relatively reduced state. This suggests that forest biomass is more carbon-rich with lower oxygen content, where high carbon content is beneficial. The CHO index values of agricultural biomass are slightly more spread out, with some points extending toward more positive values. This suggests a higher oxygen content compared to forest biomass, meaning agricultural biomass is more oxidized. The CHO index values of algal biomass are distributed around negative values, indicating a more reduced state. Algal biomass tends to contain higher lipid content which is more reduced, explaining its lower CHO index. Biomass from domestic and commercial waste shows the widest distribution, spanning from highly reduced to highly oxidized compounds. This reflects the heterogeneous nature of waste-derived biomass. The proximate and ultimate analysis results are expressed on different bases. The following 3 bases are commonly used. As received. Dry and ash-free. As received means that the biomass sample did not get any pretreatment before analysis. The results of ultimate and proximate analysis are expressed as weight percentages of carbon, hydrogen, nitrogen, sulfur, oxygen, ash, moisture, volatile matter, and fixed carbon. When the moisture is completely gasified, the constituent on a dry basis is expressed as weight percentages of carbon, hydrogen, nitrogen, sulfur, oxygen, ash, volatile matter, or fixed carbon. Ash is sometimes eliminated along with moisture. In this case, the constituent on a dry and ash-free basis is expressed as weight percentages of carbon, hydrogen, nitrogen, sulfur, oxygen, volatile matter, or fixed carbon. The figure summarizes the 3 bases. The heating value of biomass delivers information on the amount of energy that can be won when it is combusted completely. There are 2 types of heating value commonly used. Higher heating value. Lower heating value. Higher heating value is the amount of heat released by fully combusting a quantity of biomass once the products have returned to a temperature of 25 degrees Celsius. It includes the latent heat of vaporization of water in the biomass and the latent heat of generated water in the condensed state. The figure displays the higher heating value of various biomass samples, including forest biomass, agricultural biomass, aquatic biomass, and biomass derived from domestic and commercial waste. Forest biomass exhibits a concentrated range of higher heating values attributed to its lignin and cellulose content, which are carbon-rich components. In contrast, agricultural residues demonstrate lower energy density compared to forest biomass, primarily due to their higher ash content and lower lignin concentration. Algal biomass shows even lower higher heating values than both forest and agricultural biomass, largely because of its high ash content, which diminishes its effective heating value. Biomass derived from domestic and commercial waste displays the widest range of higher heating values. This variability is expected given the heterogeneous composition of waste materials, which can include paper, plastics, food waste, and other components. With differing energy content, numerous correlations for the calculation of higher heating value are available in the literature. One is that proposed by Chaniwala and Parikh. Higher heating value equals 0.3491 times content of carbon plus 1.1783 times content of hydrogen plus 0.1005 times content of sulfur minus 0.1034 times content of oxygen minus 0.0151 times content of nitrogen minus 0.0211 times content of ash. Higher heating value has the unit megajoules per kilogram. The contents of carbon, hydrogen, sulfur, oxygen, nitrogen, and ash are in weight percentage, measured on a dry basis. The correlation is valid for the following ranges: carbon 0% to 92.25%, hydrogen 0.43% to 25.15%, oxygen 0% to 50.00%, nitrogen 0% to 5.60%, sulfur 0% to 94.08%, ash 0% to 71.40%. Higher heating value 4.745 to 55.345 megajoules per kilogram. The figure shows 4 scatter plots comparing predicted higher heating value using the Chaniwala to measured higher heating value, both in megajoules per kilogram, 4 different biomass types. A general positive correlation exists between predicted and measured values, indicating the model captures the overall trend. For forest biomass, data points cluster closely around the 1-to-1 line, suggesting high accuracy, though a few outliers are present. Agricultural biomass follows a similar pattern, with strong alignment to the 1-to-1 line. Algal biomass has fewer data points but still correlates reasonably well. Domestic and commercial waste biomass shows more scattered data, but the trend still follows the 1-to-1 line. Lower heating value is the amount of heat released by fully combusting a quantity of biomass less the heat of vaporization of the water in the combustion product. Therefore, the difference between higher heating value and lower heating value is the specific heat gained from the condensation of product H2O. The relation between lower heating value and higher heating value is as follows. Lower heating value equals higher heating value minus the latent heat of water times the weight fraction of hydrogen in percent times the molar mass of water, divided by 100 times the molar mass of hydrogen. If the biomass contains moisture, the specific heat required for moisture evaporation must be added to the right-hand side of the equation. The modified equation becomes lower heating value equals higher heating value minus the latent heat of water times the weight fraction of hydrogen in percent times the molar mass of water, divided by 100 times the molar mass of hydrogen, plus the latent heat of water times the weight fraction of moisture in the biomass divided by 100. The chemical composition of ash in biomass varies due to the diverse types of inorganic matter present in different biomass sources. The elemental analysis of biomass ash can be performed in accordance with ASTM standard D3682. The table provides inorganic properties of ash samples derived from different biomass materials in weight percentages. The table shows variability in mineral composition among different biomass types. For example, rice husks exhibit the highest silicon dioxide content, suggesting they are rich in silica. Marine macroalgae has the lowest silicon dioxide content. High potassium oxide or sodium oxide in biomass can lead to ash-related operational issues in thermal processes. However, they might be beneficial for specific agricultural uses as a fertilizer due to their high potassium content. Chlorine content requires careful handling to avoid corrosion and environmental impacts in biomass conversion processes. Generally, biomass fuels have ash that is more alkaline in nature, which may aggravate fouling problems. The sustainability of a biomass conversion process at elevated temperatures largely depends on the stability and integrity of the reactor. Maintaining the conversion temperature well below the ash melting point of the biomass is essential. If the ash melts, slagging may occur, and as these molten particles cool during conveyance, they are likely to adhere to surfaces, causing fouling in the system. Preventing this phenomenon is critical to ensuring the sustainable operation of thermal conversion systems. Maglineo developed a method to determine the eutectic point of biomass. The procedure begins by producing a significant amount of ash from the biomass and forming it into pellets of a suitable size. These pellets are then exposed to high temperatures, typically between 1000 and 2000 degrees Celsius in a furnace. Afterward, the pellets are tested for compressive strength. The results typically form a bell-shaped curve with the peak indicating the ash's melting point. The theory suggests that as the ash melts, the material becomes brittle, resulting in a lower compressive strength. This peak serves as a guideline for the maximum temperature the biomass should endure to prevent slagging and fouling. In addition, Maglineo proposed a set of criteria for evaluating the eutectic point of ash in agricultural biomass. These criteria include three parameters: alkali index, base-to-acid ratio, and bed agglomeration index. The alkali index, measured in kilograms per gigajoule, is defined as the sum of the oxides potassium oxide and sodium oxide in the biomass fuel per unit of biomass energy. Alkali index values lower than 0.17 kilograms per kilojoule should have low slagging risk, and above 0.34 will have a high risk of slagging. The base-to-acid ratio is equal to the sum of iron oxide, calcium oxide, magnesium oxide, potassium oxide, and sodium oxide divided by the sum of silicon dioxide, titanium dioxide, and aluminum oxide. The potential for slagging and fouling is classified based on the value of the base-to-acid ratio as follows: low potential, base-to-acid ratio less than 0.5. Medium potential, base-to-acid ratio between 0.5 and 1. High potential, base-to-acid ratio between 1 and 1.75. Severe potential, base-to-acid ratio greater than 1.75. The bed agglomeration index is equal to the weight percentage of iron oxide divided by the sum of potassium oxide and sodium oxide percentages. Agglomeration is likely to occur when the bed agglomeration index value is less than 0.15. Biomass can be characterized by two key density parameters: bulk density and particle density. Bulk density is defined as the mass of biomass particles divided by the total volume they occupy, including the spaces between and within the particles. Bulk density is influenced by factors such as particle size and shape, moisture content, particle density, and surface characteristics. The standard method for determining bulk density is outlined in ASTM 873-82. A rigid box with known dimensions, typically 305 by 305 by 305 mm, with appropriate handles and a weighing scale accurate to within 100 grams, are used. After measuring the weight of the box, a biomass sample is poured into the box and dropped from a height of 610 mm, approximately 5 times to allow for settling. Additional biomass is added and excess biomass is removed using a straightedge device. The box and sample are then weighed. The bulk density equals the weight of the box and sample minus the weight of the box divided by the volume of the box. Biomass with a higher bulk density is more suitable for long-distance transportation due to its reduced volume despite its heavier weight. Wood typically has a bulk density ranging from 300 to 550 kg per cubic meter. Biochar has a lower bulk density, usually between 200 and 300 kg per cubic meter. Rice straws and hulls have an even lower bulk density, around 70 kg per cubic meter. Densified products like briquettes can have a higher bulk density ranging from 700 to 800 kg per cubic meter. Particle density refers to the weight of a biomass particle per unit volume that it occupies, representing the density of the particle itself. The void spaces between individual biomass particles are not considered. Particle density equals particle mass divided by particle volume. To determine particle density, a specialized device called a pycnometer is used. This device measures the volume of void spaces by employing an inert gas, such as helium. The procedure is straightforward. A ground and dried biomass sample is placed in a receptacle with a known and calibrated volume. The receptacle is then sealed in a system where a complete vacuum is created to remove all void spaces. Subsequently, the voids are filled with a measured amount of inert gas. The volume of the biomass is calculated by subtracting the volume occupied by the inert gas from the total volume of the receptacle. The compactness of a biomass sample can be assessed by comparing its bulk density to its particle density. To enhance the transport efficiency of biomass and reduce fuel consumption during transportation, biomass is often densified through processes such as briquetting or compaction. The spaces within bulk biomass samples are described by their porosity. Porosity equals 1 minus particle density divided by bulk density. The shape and size of biomass feedstock particles influence mixing and fluidization, the surface area available for heat and mass transfer, and the flow behavior of the particles. Consequently, feedstock with varying shapes and sizes may exhibit differences in conversion efficiency and energy input requirement. Pretreatment is typically performed on feedstock to meet the specific requirements of different thermochemical conversion technologies. Particle size distribution is used to determine the average particle size of ground and dried biomass samples. The particle size distribution of biomass is measured using a set of standard sieves, such as Tyler sieves paired with a motorized shaker and timer. Tyler sieves are available in standard sizes ranging from 37 micrometers to 3,360 micrometers. The shaking process typically takes between 15 and 20 minutes. To measure particle size distribution, a known weight of ground biomass is placed on the topmost sieve in the stack and shaken for 15 minutes. After shaking, the weight of biomass retained on each sieve is recorded. The fraction corresponding to each size range is then calculated. Heat capacity is a critical thermal property of biomass often used in thermodynamic calculations. It varies based on the moisture content of the biomass and the temperature. There is a consensus that biomass-specific heat capacity increases proportionally with temperature. DuPont provided a correlation for the heat capacity of dried agricultural residues with particle sizes below 200 micrometers over a temperature range of 40 to 80 degrees Celsius. Heat capacity equals -299 plus 5.34 times temperature. where heat capacity is in joules per kilogram Kelvin and temperature is in Kelvin. For various wheat and wood biomass samples, the heat capacity ranges from 1,300 to 2,000 joules per kilogram Kelvin within a temperature range of 40 to 80 degrees Celsius. For biochar derived from the same materials and treated at 500 degrees Celsius, the heat capacity is narrower, ranging between 1,127 and 1,193 joules per kilogram Kelvin. Biomass materials with higher thermal conductivity facilitate greater heat transfer compared to those with lower conductivity. This parameter is also important for preventing autoignition in storage bins for dry biomass. Biomass is inherently anisotropic, meaning its thermal conductivity varies depending on factors such as the direction of heating, moisture content, porosity, density, and temperature. The thermal conductivity of biomass varies significantly. For example, softwood exhibits 0.099 watts per meter Kelvin. Maple biomass exhibits 0.419 watts per meter Kelvin. Determining thermal conductivity of solid biomass follows methods similar to those used for polymers and plastics. A heat source is applied to one end of a reference piece and a heat sink to the other. The axial temperature gradient across two reference pieces is measured. The heat flow in each is then calculated. The average heat flow through the reference pieces is used to evaluate the test sample. By considering the dimensions and temperature differential, the thermal conductivity is determined. Research indicates that torrefied biomass such as torrefied pine and black pellets exhibits significantly higher thermal conductivity than untreated wood materials. The PowerPoint file, the manuscript for the presentation in Word format, and the data source containing ultimate and proximate analyses of more than 1,000 biomass samples in Excel format can be accessed via the QR code or the link in the video description.